Hello and welcome to Texture Sampling Part 2. This is a follow-up video from Part 1, and if you haven't seen that then I suggest you go and do so now, because we're going to carry on exactly where we left off. You will recall that we built a little framework application where we could load a texture and zoom in on it. And as we zoomed in on it, we noticed that the individual image's pixels turned into small squares, and as you keep zooming in, it starts to look a bit blocky. At the moment, everything was done with point sampling. We take the infinitesimally small pixel of the texture, and as we zoom into it, we give it area. We form a small rectangle. This allows us to address within the space of an individual pixel. It is sub-pixel sampling, and this is the cause of all of the problems that we're going to see today. Specifically, we're going to look at two approaches. The first is called bilinear filtering, which looks like this. So that is an improvement, but there are artifacts. And we can improve upon that with bicubic filtering, which looks like this. The artifacts are no longer as pronounced. The image looks reasonably well sampled, but we pay a price for this performance increase. Now, two things in this video, we're specifically interested in zooming into textures, and following up from the comments of the last video, shorter videos seem okay, so with that in mind, let's get stuck right in. Today I intend to show two types of interpolation, but because we're trying to do this in multi-dimensions, it gets a bit tricky to do this in OneNote. So I want to make a bold assumption to begin with, and that is we're working with single channel data. So here I have a 2D array which represents my texture of pixels, and each pixel would usually be an R, G and B value. Today we're just going to assume they are a single colour. Intensity. And if I was to take a slice through my texture like this, I may end up with a graph like this, where these values could be, say, pixel luminance values from 0 to 255, and along the x-axis here we have the pixel's location along that x-axis. So we're going from medium level to a dark pixel to a very bright pixel to medium level again and then to a slightly brighter pixel. Conceptually, in the image, the pixel is arealess. It is an infinitely small point of information, its colour. However, as soon as we start to zoom in on the image, we have to give it area. And we looked at how when we take a denormalized coordinate, it can exist anywhere within this space. And we can bin that to the appropriate pixel value. And for the point sampling we did in the first video, we took the floor of the denormalized coordinate in the image's space to give us the precise x, y location of the pixel we were interested in sampling. This resulted in any sample within the image space, giving us the correct pixel value for that location, and when we rendered the image, we see that the pixels look like little squares, and this isn't surprising given that each sampled value occupies a whole area. Representing the image as lots of little squares can be a bit jarring, and so we're going to interpolate between the sampled pixel values. And the easiest form of interpolation to get started with is linear interpolation. It is a straight line, or as straight as I can draw them anyway. Now, I've talked about linear interpolation hundreds of times. It's used in almost every OneLoneCoder video. And I usually describe it like this, that given 2 points, we want to find a third point somewhere along that line. And normally, we would normalize that line to be represented by a parameter called t. And so, if t was equal to 0.5, then that is halfway along the line. If it was 0.25, then it'll be a quarter of a way along the line. This is quite nice because a t of 0 would be equal to p1 and a t of 1 would be equal to p2. And so if we were to call our point to be discovered a, we would normally use an equation of the following form. A equals p1 plus p2 take p1 multiplied by our parameter t. This gives us our starting point, our gradient, and our parameter. And it's analogous to the line equation y equals c plus mx, which you might have learnt in high school. And before I continue, I should point out, of course, that p in this case is equal to an x-y coordinate pair. So whatever we do for x, we do for y. Now, this format always assumes that we start at 0 and we end at 1 for t. But I want to rearrange this slightly, just to illustrate a different way of thinking about t. I like t. So I'm just going to expand out these brackets, p1 plus p2t, take p1t, rearrange, so now we've got p1 take p1t plus P2t, and finally take the t out, so this would be 1 minus t P1 plus, and I'm going to write it a bit strangely, t P2. This is actually another common form of linear interpolation. It's actually one more computation than the original form, as here we can see we've got an addition and a subtraction and a multiplication going on, as opposed to a subtraction, a multiplication, and an addition. This seems much worse, but conceptually it's wonderfully illustrative. We can see that as t tends towards 1, we take the full value of P2. And if t tends towards 1 for P2, it must tend towards 0 for P1. What we have developed here are sometimes referred to as basis functions. So let's label our basis function Q1 and make it equal to 1 minus t, and we'll have Q2 simply equal to t. They're very simple linear functions. Therefore, we can finally write that a is equal to Q1 P1 plus Q2 P2, which is a little bit of a digression, but we'll see why this is interesting later on. And you can tell this is an old school one lone coder style video because here we're back in desmos.com, one of my favourite websites, and it's had upgrades to allow all sorts of interactivity. I've implemented our basic points here, P1 and P2, and now I can move those around on the graph. All those years drawing this by hand, and look at this. I've also added in Q1 and Q2, which are our basis functions, and I've limited them to between 0 and 1. We can see those plotted here, and as I mentioned, they're linear. The green line represents Q2, which means as we increase in t along the x-axis here, we take more of that point, and conversely, we take less of P1, the blue point. I then draw that function here with the y equals Q1 P1 plus Q2 P2. And so as I move the points around, this is all being calculated in real time. The red line is the resultant linear interpolation of t between 0 and 1 and my 2 points. So why is it interesting to represent t as a basis function like this? Well, by pulling t out, we don't have to use it linearly. We're going to use it linearly for the rest of this video, and this is definitely a bit of a divergent path, but we could use t in non-linear ways. So let's take Q2, for example, and instead use t squared. Here we've got the parabola, and we look at our interpolation, and what we have now is some sort of weird curve. The structure of the interpolation equation has remained the same. Our points have remained the same. But by non-linearizing the interpolation, we're getting funky, weird effects. I like that. But yes, Javid, going completely off topic. Hopefully you can see now that the points in our sampled image are simply P1 and P2 for given neighbouring pixels. But seeing it drawn out like this shows that something's not quite right. There's a lot of error. This first pixel looks just fine, but this second pixel is underestimating. Lots of error. This third pixel, well, that's almost entirely wrong. Pixel 4, again, is underestimating. And pixel 5 is overestimating again. Whenever we start doing bilinear interpolation like this, we're fabricating data. And whenever we fabricate data, we're going to introduce error. If we accept the fact that we can't get rid of error entirely, we should aim to try and minimize it. Our sample points are currently at the left-hand edge of our individual pixels, and this is because we were taking the floor function. That was fine for point sampling. Instead now, I'm going to take the middle of the pixel. Since we've now given the pixel some area, we can take its middle. And if we linear interpolate between the middle of the pixels, again with my shaky one lone coder hand, what we see now is at least the error is balanced out and shared amongst the pixels. And we'll start coding this up in just a few seconds and we'll see the consequences of this. What I've been talking about so far is just linear interpolation. That's basically a 2D solution to a 2D problem. When we start working with an array of data like a texture, we've got an additional dimension to think about. Let's put in a denormalized texture coordinate somewhere in this image. Here, this is the point I wish to sample. Whilst we've been thinking about this, we've been looking at how we would sample it in the x-axis, but we also must factor in how we sample it in the y-axis. And hopefully you'll be able to see that one relies upon the other. To solve this, I need to do several linear interpolations. Firstly, I'm going to get P1 as a regular point sample. I know I need to interpolate towards my neighbouring pixel values. So I'm going to take my right-hand neighbour and use that point sample value as P2. Recall that the decimal part of my denormalized coordinate refers to where the sample point exists within the given pixel space, and that because all of our pixels are precisely 1 unit by 1 unit apart, we can use this value directly as our t value, in this case in the x-axis. By linear interpolating between P1 and P2 with t of x, I'm going to get a point along the top of my pixel, and I'm going to call that top x. As well as x, we're also interpolating in y, which implies I need to know this point somehow, but I'm not there yet. To get this point, I need to linearly interpolate along the bottom edge. So this would be between P3 and P4. Using the same x value as before, gives me my bottom x value. This top x and this bottom x are pixel values in their own right. I can now interpolate along the y-axis using this top and bottom x value as my start and end points. So this time we start interpolating between top x and our bottom x with respect to ty, which results in our final pixel value. So in short, we linearly interpolate here, we linearly interpolate here, and finally, we linear interpolate in this direction. This interpolation in both x and y is called bilinear. Let's code this. Carrying on from exactly where we left off, I've added to our sample method enum class a bilinear clause and a bicubic clause. And in our sample function, I've added those case statements into our switch of the sample method. Recall that the sample function brings in a normalized coordinate and multiplies it by the dimensions of the image to give us a denormalized coordinate. When we were point sampling, we simply took the floor of that denormalized coordinate to get the integer component of it. With bilinear sampling, we're going to do pretty much the same, but I'm also interested in retaining the decimal part of that denormalized coordinate, because that will be a value between 0 and 1, and given that all of the pixels in our image are the same width and same height, that offset value indicates how far into the pixel I need to sample. Now I needed to sample my 3 immediate neighbours. I need to point sample 4 different cells. This is the cell that I have naturally landed in, this is my right hand neighbour, and these are the 2 cells below and to the right. You can see I'm getting the location by simply adding a small offset to their position. Once I've sampled these points, I can create interpolations along the top and the bottom. And here we can see the equivalent of P1 times Q1 plus P2 times Q2. They're our basis functions, and I'm using the offset in the x direction as my t value. With the top and the bottom values in hand, I can now interpolate along the y-axis to give me my final pixel value. This time using the y component of my offset as my ty value. So there you are, not very complicated. Let's take a look. Here is my image with point sampling, and I'm going to zoom in, and if I press the 6 key, which is mapped onto bilinear sampling, we can see certainly the image has gone blurrier. The sampling has worked. I can switch back to point sampling by pressing 5. I can flick between the two, but the first thing that strikes me is that the whole image is shifting by 1 pixel. Let's have a look at one of our corner cases. So we're in point sampling now. I press 6. We can see that the sampling is getting it wrong by half a pixel. This is because we haven't taken into account the half unit error, which I showed in the slides. So let's throw that in. But it's quite nice that you can intuitively see why the error exists. As we're sampling up to the red pixel, we're transitioning from blue to red. Once we're in the red pixel, it's red to red, and that works quite nicely. But if we go to the end here, we end up in a situation where we need to transition from red to black. And everything happens with this top left bias. This is easily fixable by adding in a half pixel offset. to take into account that we should be sampling from the middle of our denormalized pixels. Now let's take a look. I'll zoom back into the top left corner of the image. We're in point sampling mode now. If I press 6, well, there we go. Aesthetically, it looks about right. It's staying where it should be. Let's have a look at some of the other qualities of this sampling method. If we go down to our grids, when I turn on bilinear filtering, we can see that the grid becomes, well, a bit diamondy. And if we go to natural parts of the image, they look quite good, but there's a staircase-like effect. If we go to the artificially noisy parts of the image, we see the combination of the staircases and the diamonds. It does a nice job. It's reasonably computationally cheap, but I think we can probably do a bit better. We can have a look at the performance. Don't forget we put in a way of measuring it. So in point sampling mode it's taking about 3 to 4 milliseconds per frame, and with bilinear sampling it's taking about 15 to 16. There's no doubt about it then, we are paying the price for smoother looking imagery. Even though bilinear sampling is almost ubiquitous now in all sampling problems, there's no getting away from the fact that when we try to compensate for the error, we end up with these pointy middles of the pixels, and straight lines between neighbouring pixels. This gives us those staircases and diamondy sparkles. Perhaps a better way is to round off the corners of the pixels instead, with something like this. So we round down and across. This way, our error is far smaller, but the transition is less jarring. In fact, if we did use a function which basically created some sort of sigmoid shape, where a sigmoid kind of looks like that, between each pixel, even though the data may have less error, the artifacts are still going to be quite vibrant. What we'll see is instead lots of little circles and sort of circular-like spirally staircases instead. In both of these cases, the problem is because our sampling method is information starved. Instead, it would be nicer to find some sort of curve that smoothly goes through all of these points. Deriving a function for such a curve is staggeringly complicated, but we can simplify by approximating considerably using splines. Yay! We like splines on this channel. In fact, we like splines so much that I have 2 videos already dedicated to the Catmull-Rom cubic spline. And it's exactly this spline that I'm going to use as part of my bicubic interpolation strategy. A word of warning though, if you do go and watch these old videos, they're a little bit more stilted than the ones you see today. To use a cubic spline to interpolate between 2 points, and it must go through those 2 points, we'll call these P1 and P2, we also need neighbouring information, so P0 and P3 in this case. In the context of image sampling, like before, I'm assuming that the distance between the points is simply 1. And so I can use the offset into the pixel to give me any point along that curve. The neighbouring points are used to influence the gradient of the curve going through the control points. Therefore, the neighbouring pixel intensities play a role in how well this section of the curve is constructed. Now, the reason I spent so much time talking about basis functions before is that for linear interpolation, we just had 2 components, P1, Q1, and P2 and Q2. Since we're introducing 2 additional points, we're going to also need to introduce 2 additional basis functions. And for a Catmull-Rom cubic spline, these are Q1 equals minus t cubed plus 2t squared minus t, all divided by 2. And straight away you can see that the introduction of the power of 3 here makes this a polynomial. It's not linear anymore, and it's cubic. It's a cubic spline. Q2 equals 3t cubed minus 5t squared plus 2. Again, divided by 2. And again, it's cubic. Q3 equals minus 3t cubed plus 4t plus t. Again, divided by 2. And finally, Q4 is simply t cubed minus t squared divided by 2. In the splines videos, I try to demonstrate why these basis functions are the way they are. The derivation is quite complex, and you can blame Mr. Catmull and Mr. Rom for that. But the result is that for a given t between 0 and 1, we will definitely go through P1 or P2. And because I've been on a bit of a Desmos kick since discovering it's got all of these new features, I went ahead and implemented it again. Now, one of the important features this time, we must make sure that the distance in the x between our points is the same. This makes our image rectilinear. The spline itself doesn't have to obey that law, but for image sampling, that's exactly what we're doing. So this time, I can move my points up and down, but I can't move them left or right. Now, the nice thing about the Catmull-Rom splines, if I line them all up in a straight line, we get a straight line as the result. If I line them all up in a straight line at an angle, see if I can do this, about there and this one up here, again we get a straight line. Perfect. This is going to work very nicely in situations where the linear interpolation was correct. If I put these two as the same and these two low, we see we get this parabolic trajectory. Even though we're using cubic basis functions, it can quite happily accommodate power of 2 curves. We also start to observe something interesting here. In theory, our pixel value is luminance in the y-axis. It shouldn't be above the green or blue value. But because we're putting a constraint that the gradient must be towards the red and orange points, then it has to curve upwards. We've gone beyond the value of our original pixel. We've effectively made this pixel brighter. This is something we've got to be aware of. Now, the pixel game engine will handle this. It will automatically saturate pixels rather than letting them wrap around. It may also mean, of course, that our pixels can go below 0. Now, when we're working with the pixels' values during all of these equations, we need to allow that to happen. It's just the final pixel result we need to ensure is within the range 0 to 255. Like with the linear interpolation, I've drawn in the basis functions themselves, although these are explained in the other video. So that was a cubic interpolation in 2D. How do we handle a bicubic interpolation when we're sampling the image? Well, let's pick the same sampling point as before. Therefore, we know our tx and we know our ty values. We also know that we needed to sample P1 and P2. Well, you've probably already guessed, but now we need P0 and P3. And this will give us a single point somewhere there. I've marked it in yellow. So if we cubic interpolate between P0, P1, P2, and P3, with respect to Tx, we're going to get our y P1. Now, my notation's getting a bit crazy here, but that means for our yellow line going down, we're basically getting P1. That implies that we're also going to need points at these locations too. In our y-axis, this would be P0, P2, and P3. Well, this means we've got a lot more interpolation in the x-axis to do. And indeed we do. We've also got to get these 4 points, and these 4 points, and these 4 points. In total, we've got to sample 16 points of our image, and we'll need to perform 5 cubic interpolations. The first one is here, then here, then here, then here, and that would give us 4 new control points for a final spline along the y-axis that we can use with respect to our ty to give us the point we're interested in. Conceptually, this is all very similar to bilinear interpolation. We've just got more to do. In 2 dimensions like this, this is bicubic sampling. So let's code that up. Just as with bilinear, I need to work out the cell coordinate and the offset coordinates. Now, this is where things are going to get a little bit strange. The built-in pixel game engine pixel type will render any mathematical operations applied to it subject to clamping it to the range 0 to 255. This is almost always desirable, until you want to start doing weird maths with pixel values. So I'm going to create an intermediate pixel value structure called a float pixel for the red, green, blue and alpha components. You saw that I need to create a 4x4 array of points to point sample from the image. The 16 points I can iterate through with 2 nested for loops. And in this instance, I'm gathering the point, and then I'm converting it over to my floating point pixel type by casting the integer component values to floats. I now need to calculate my basis functions. Now before they were just linear, so in the bilinear function, we didn't need to break them out, they're just part of the equations. But that's going to get a bit unwieldy now. Since it's a cubic, I know that I need to take my t values from the offset and square them and cube them. Now, curiously, I'm doing this with a 2D vector because this will do element-wise operations. So my vt here is the t value in both x and y independently. It goes without saying then that my t cubed value gives me the t cubed value in x and y independently too. I went through the basis functions on the slides, but I've just implemented them directly in code here. Q1, Q2, Q3 and Q4. The 16 points that we used originally were to calculate 4 final control points to do a cubic interpolation in the y-axis. So I need these 4 final points storing in my floating pixel type. For the 4 cubic splines that I now need to compute, I've simply got P1 multiplied by Q1. P2 and Q2, P3 and Q3, and P4 and Q4. It looks like a lot more because I have to do this for every single colour component of the pixel value. This has finally given me 4 control points along the y-axis with which I can compute one last cubic spline. I'm going to clamp the range of it and convert it back to an unsigned integer between 0 and 255 to give me my complete output pixel. On the surface, bicubic interpolation seems a lot more complicated, but it really isn't that much different to bilinear. We've just expanded on the number of basis functions. The complexity has been added because we've needed an additional type to support the mathematics, so we don't get any sort of awkward rounding errors due to integer mathematics. However, the side effect of doing it this way has demonstrated just how much computation needs to be performed per sample. This was somewhat hidden in the bilinear implementation, because the Pixel Game Engine built-in pixel type supports operations between pixels. If I multiply a pixel by a constant, it will automatically handle all of the components. We've needed to do that explicitly this time round. But it's a nice visual example of just how much more computation effort bicubic sampling is going to require over bilinear and ultimately over just simple point sampling. Well, now we've gone to all of this effort, I suppose you want to take a look. I've mapped bicubic sampling onto the 7 key being pressed. So let's zoom in, let's see some rectangles in point sampling mode. And now I'll do bicubic sampling mode, and straight away, it's very difficult to identify any visual artifacts. We can see it's gone blurrier. Of course it has to go blurrier, we are making up information. But the ladder effects and the sparkles we saw before are definitely minimized. So let's try point sampling, bilinear sampling, and cubic sampling. And if I flick between bilinear and bicubic, we can see the overall image quality is about the same, but with certainly less artifacts. Sorry, certainly fewer artifacts. If I go to the grids are far more encouraging too. So this was point sampling, this is bilinear sampling with the diamonds, and bicubic sampling has kind of brought it back. Now the grid would give us an example of that sigmoid-esque error artifact that I was a bit worried about, and this is because this is an extreme scenario, but it still looks better. And if I go and look at some natural noise in bilinear mode, it's diamondy. In bicubic mode, well, it just really looks more like a contrast enhancement. I'm sure that's not the right word for what it's called, but the image just looks clearer. Let's finally go and have a look at the edge case we've been using. So this is in bicubic and now looks very nice. So this is a good example of how the pixel has a nice curvature blending it into the background. We go back to bilinear, they look like straight linear ramps instead, and of course point sampling. So between the two, that looks pretty good. In terms of performance though, we are paying a heavy price, which is to be expected. So here in point sampling mode, we said it was about 3 to 4 milliseconds. In bilinear sampling mode, it's about 15 to 16 milliseconds. And now in bicubic sampling mode, it's 26, 30 odd milliseconds per sample in this arrangement with this configuration. Of course, there's been no attempt to really optimize anything here. And that's really it for this video. In the next part of this series, we're going to look at what happens when we start to zoom out of textures, where we can begin to see artifacts that are unpleasant and weird stuff happening. We did kind of touch on that in video 1 too. Anyway, if you've enjoyed this one, give me a big thumbs up please, have a think about subscribing. There's a live demonstration you can play, the link is below. Come and have a chat with me and others on the Discord server. It's a lot of fun. I'll see you next time. Take care.